Thank you. So this is the main part of the presentation. So I wish to think about the relation between what is called a modular parameterization in the context of arithmetic geometry and the Polyakov path integration that we do in string theory calculations. So this presentation is based on a joint work with Satoshi Kondo and based on two preprints in 2018 and 2019. I myself have background in particle theory, and Satoshi Kondo is an expert in arithmetic geometry. So this is the combination of us. So here is the plan of the main part of the presentation. I begin with the review on mathematical background using 8 slides, and that's going to cover the notion of the arithmetic models, Galois representation, stuff that are going to be very tough for me to talk about it. But anyway, I have to do it. That's not my field of expertise, but I'm going to try. And after that, after explaining those materials briefly at least, and then I wish to discuss how those modular forms that are associated with the elliptic curves in the context of arithmetic geometry can be reproduced by the genus 1 correlation functions in string theory. I'm going to use 6 slides, and then if time remains, then I have prepared 3 slides for discussions. All right, so let me begin with the mathematical background introduction. So I need to start with the notion, explaining the notion of arithmetic models. So the most natural way for string theorists to understand the elliptic curve is a complex analytic manifold obtained by taking a quotient of the complex plane divided by a rank 2 free lattice. So the complex parameter z is going to be the complex structure of the target space elliptic curve. And in the case when we choose the complex number z to be I, so it is to take a quotient of the complex plane by a square lattice. And then it is known that its algebraic geometry description has this defined equation. At least we can choose in that way. And then the J invariant is calculated, and we know that the J invariant is 1728. That's the way to see most naturally for string theorists, and they have equivalent information. Although we could think of other defined equation for in CP2 or any other projective space over the complex number field, and yet there is the isomorphism defined over complex number. So they have the equivalent information, and that's fine. But when we begin to see things in different way, and then there are different observations. So in that geometry, the ring of regular functions is given by this ring, the polynomial ring divided by the ideal generated by this x cubed minus x minus y squared. Well, we could change the defined equation from this by inserting the factor 2 here in front of x. Then the ring of regular function is this. And yet they are the same geometry. They're the same. Those two rings are isomorphic because we can substitute s by x times the square root of 2 and stuff. And then those two rings are isomorphic. So that's another way to say that the two varieties defined by those two equations are isomorphic over the complex number field. But we could think of the algebraic geometry over the field of rational numbers as well. This is because the defined equation chosen in that way happen to have all the coefficients being in the field of rational numbers, Q. So we may think of the ring of regular functions of an arithmetic variety defined of the field of rational numbers in this way. And we could also think of a ring of regular functions in this way with the coefficient 2 inserted. Then actually this ring and that ring are not isomorphic. We cannot find an isomorphism without introducing some stuff like a square root of 2 and to establish the isomorphism between them. This is a warning for the prevention of the COVID actually in Kashiwa. So here's the notion of the arithmetic model of a complex number, the variety defined of the complex number field. So suppose that we have a variety x defined over the complex number field. It's like the subvariety of a complex projective space defined by given by the defining equation, where we might use the complex numbers of the coefficients of the defining field of definition. So, but still, for that complex complex variety, we can think of a notion of arithmetic model for any number field which sits in between the field of rational numbers Q's and the field of complex numbers. So that's K. So we may think of the variety of the field of rational field of the number field K in such a way that when we allow to tensor the complex number field to the ring of the regular functions of the variety X, and then we might recover the variety or the ring of regular functions over the complex number field. In that case, we call this variety X over the field of number field K as an arithmetic model of the original variety X. And the field K in that context is called the field of definition. A warning comment is that for given the variety defined of the complex number field, and for any given the number field K, it is possible that there is no such an arithmetic model available. But sometimes for given complex variety and also a specified number field K, sometimes there may be infinitely many arithmetic models whose tensor C reproduces the original variety over the complex number field. So that's a notion of the arithmetic model of a variety defined over the complex number field. So suppose that we have an arithmetic model, and let me think of the more restricted case where the variety is an abelian variety rather than a most general variety. And suppose that the abelian variety is defined over the number field K, which sits in between Q and C. And then within this abelian variety, well, that looks like elliptic curve though. And then there are torsion points, 2 torsion points, 4 torsion points, stuff. And it is known that those torsion points have their values, coordinate values in the extended number field. Those points may not have their values within the K itself, but still they have their values within the algebraic extension fields of the field K. So those torsion points may be decorated in different color depending on which extension fields they have their values in. Fine. And then we may think of the Galois transformation by any element which is identical over the field of definition K. And then, well, for points whose values happen to be in the original field of definition K, they will remain there. But other torsion points whose value were not in the field of definition K, but in the extended field, may be exchanged by one another. So the Galois transformation induces a permutation among those torsion points. And it happens actually that transformation rule can be described as the multiplication of a matrix, a property matrix on those Elliptic modules. And so this understanding allows us to construct a representation of the Galois group over the field of definition for a given algebraic variety like abelian variety. And then for a given variety, and then we have the representation of the Galois group. And from those ideas, what is called L function is defined. There are two different ways to characterize or define those what is called L functions. One way to go is to use the congruent zeta function, which relies on counting the number of points in a given field extension, and use Weil conjecture. And the other way to introduce the L function is to use the notion of the Galois representation itself. And so let me go with it in this presentation. So in the number field K, there is a well-defined notion of the ring of all the algebraic integers in that given field. And that is denoted by O sub K. And that's a generalization of the ring of integers within the field of rational numbers Q. So this is similar notion as Z. And then we may think of the list of prime ideals of the ring of algebraic integers in K. Just like we think of the prime ideals of 2 generated by 2, 3, 5, 7, 11, stuff. And then it is known that for each one of those prime ideals, there is a specific element in the Galois group called Frobenius, and then we may think of its representation over the Tate module, and then in this combination with the argument S, we can define the L function as a function of S. So this information encodes all the representation of the generators of the Galois group. The denominator here is a characteristic polynomial of the representation matrices of the generators of the Galois group. So the L function is meant to be a kind of the creature that captures the information of what kind of the Galois representation is produced by the variety defined of the number feed K. So that's the idea of the L function and the Galois group. Now let me go back to the easiest example of the elliptic curves with the complex multiplication. So let me go back to the category of complex analytic manifolds, and then the notion of the elliptic curve having complex multiplications is defined in this way. So here's an example of an elliptic curve presented as the quotient of the complex plane over a rank 2 free rank 2 lattice generated by 2 and the 1 plus square root 5 times I. So that's the unit cell. The red one is the unit cell. And for this specific elliptic curve, actually, there is a very special operation of multiplying square root 5 times I to the complex coordinate here in the complex plane. And then this unit cell is rotated away to the other, well, it's not unit cell, parallelogram, described by the dashed line in red. And so because all the vertices are on the lattice point, so this defines the surjective map from this elliptic curve to the elliptic curve itself, but it is not 1-to-1, but actually it is a 5-to-1 multiple covering map. And the elliptic curves in complex analytic, in the category of complex analytic manifold, it is called the elliptic curve with complex multiplication if the ring of those non-trivial complex multiplications are denoted by O, it is strictly larger than the ring of integers. We always have the choice of multiplying factor 2, factor 3, factor 4. So we always do have the ring of integers as in complex multiplication. But whenever we have the non-trivial complex multiplication, we say that the torus has complex multiplication. And it is known as the basic facts that the field of fractions of this ring O for elliptic curves with the complex multiplications is one of the unimaginary quadratic fields. It is a field, degree 2 extension of the field of rational numbers obtained by joining the square root of minus d. D is a square free positive integer in this way. And let me skip it. And so that's the characterization of the complex multiplication. And the other complex multiplication, the characterization of a complex multiplication, which is known to be true in the case of elliptic curves, is that, well, we do know that the complex structure parameter z, which is also regarded as the ratio of the period integrals, is the root of a quadratic polynomials with the coefficients being integers. So the ratio of the periods are indeed algebraic. But also we may impose the condition that the J invariant of the elliptic curve is also algebraic. And then the common subset happens to be actually equal to all the complex, the elliptic curves with the complex multiplications. So in the case of CM, J invariant is algebraic. And when we impose the elliptic curve has an algebraic J invariant and also the period ratio is algebraic, and then it is CM. There is a theorem back in 1937. So that's a characterization of the elliptic curves with the complex multiplications. And then, I'm sorry. And I showed you earlier that actually there are two elliptic curves with the complex multiplications which share the same ring of complex multiplications. And so we may group together the elliptic curves with the complex multiplications when they share the ring of the complex multiplications. And when the ring of complex multiplications is equal to the ring of all the algebraic integers of the field of quadratic imaginary field K, and then it is known that this set is one-to-one with the what is called the ideal class group of the field imaginary quadratic field K. And also the Galois group acts on this set by the carrying out the Galois transformation on the defined equations. And then this set of elliptic curves form an orbit under the action of the Galois group. But it is further known that this action factors through a quotient, which is a finite group over the Galois group of what is called Hilbert class field over the field of the field K. And I'm not explaining what is the Hilbert class field in this presentation, but this is the example in the case where the imaginary quadratic field of complex multiplication is Q with the square root of -5. And then the Hilbert class field is this field. And those two elliptic curves with the complex multiplications are in one-to-one with the non-trivial ideal classes of the field K. So I've explained the upper half of the first slide in this presentation. And now, so let me talk about the arithmetic models of those complex elliptic curves with the complex multiplications, or CM elliptic curves for short. So, so it is known first that well, there are models, arithmetic models of a CM elliptic curve when the field of definition K is contains what is called Hilbert class field. So that can be regarded as the characterization of this field. And when our arithmetic model is given, and then what is called a Hecke character is assigned to that model. With those two properties, I'm not going to explain what is Hecke character or what are those properties, but those details do not matter so much. Well, actually do not matter in the rest of the presentation. We just need to know that a stuff that is called Hecke character is assigned to an arithmetic model, and that's enough. And so, and the converse is also true in the sense that if we choose the field of definition K to be an abelian extension containing the Hilbert class field, and if I specify one element in this set of CM elliptic curves, and then there is one-to-one correspondence between the set of Hecke characters satisfying those properties and the arithmetic models modulo isomorphism over K. And so, so the classification of the arithmetic models over the certain given field can be converted into a classification of Hecke characters. And that saves our life enormously, because it's going to be a very difficult task to write down all possible defining equations in a number field and try to find and identify all possible isomorphism among them. That's a really tough business to do. But the classification of Hecke characters is much easier because that's just purely algebraic. So that has almost explained what I wrote here. For given elliptic curves with complex multiplications, there are actually infinitely many arithmetic models defined over the Hilbert class field. All right. And then let me introduce another idea called the elliptic curves of Shimura type, which is a special class of arithmetic models for elliptic curves with the complex multiplications. So here's the definition. So let me focus on the situation where the field of definition is an abelian extension of the imaginary quadratic field K, and also I assume that it contains the Hilbert class field of that K. And then its arithmetic model is said to be of Shimura type. And when one of the following three conditions are satisfied, and they are known to be equivalent conditions. There are so many jargons in arithmetic geometry, and I've not tried to explain all of them. But the one important characterization is the second one, which is that it is possible to construct a Galois representation of the Galois group of the field of rational number, the field of the mathematical quadratic field K. The Galois representation of the field of definition K is well defined already, as I've explained earlier, on the Tate module of the elliptic curve E itself. But when we think of the induced representation of that to define the Galois the representation of the Galois group of the field K, and the representation space in that context is known to be the Tate module of what is called the restriction of the scalar of the original elliptic curve E. I'm not going to explain what it is, but it is still an abelian variety. And so Tate module of that abelian variety is a sensible notion. And the representation space of the Galois group as the induced representation is known to be this representation space. And that's a general story for the arithmetic model of a CM elliptic curve. But an arithmetic model is said to be of Shimura type when the representation of this group splits into one-dimensional representations in this way. So that's the characterization of the models of Shimura type. And another characterization is that I said earlier that there is to arithmetic model, one Hecke character of the field of definition K is assigned. But for those Hecke character, there are the multiple Hecke characters of the field of the imaginary quadratic field of complex multiplication exist in such a way that this relation holds. I'm not going to explain what it means in detail, but there are those two characterizations. So one is to see that to impose a condition that the representation of the Galois group splits into one-dimensional representation. And the other is that there are Hecke characters corresponding to the original one of the elliptic curve. So I've already introduced the notion of the elliptic curves of Shimura type. So we can go back to the question of what kind of L function those varieties have. For general arithmetic models of an elliptic curve of complex multiplication, and then it is known back in 1953 that the L function, which is the characteristic polynomials of the generators of the Galois group of the field of definition K, it can be obtained as a product of what is called L functions of the Hecke characters. I'm not going to explain what it is because those details do not matter so much. And that was a general story. But when it comes to an arithmetic model of Shimura type, and then what is called the L function of a Hecke character further factorizes in this way. So here, so what we have on the right-hand side is the product of the L function of the Hecke characters of the field of the imaginary quadratic field K. And I said earlier that there are Hecke characters of the field capital K exist. And so those phi alphas are those Hecke characters. And those factorizations of the L functions correspond to the fact that the representation of the Galois group splits into one-dimensional representations over this representation space. And the one-dimensional representations of this Galois group of K are in one-to-one correspondence with the Hecke characters of the field capital K. So, and furthermore, for individual one-dimensional representation of the Galois group of the field K, we may think of the two-dimensional representation of the Galois group of the field Q as an induced representation. Incidentally, the L function here for Hecke character phi alpha is known to be a Mellon transformation of the Hecke, what is called Hecke theta function of the Hecke character phi alpha, which is denoted by F alpha. And it is known that this Hecke theta function is a weight to cusp form. So here we have a pair of two-dimensional representations of the Galois group of the field Q, and also we have weight to cusp forms. Those pairs are generated by elliptic curves of Shimura type. So let me put this in the context. By the way, I'm sorry, before getting that. So I said earlier that for those arithmetic models here and there, the weight to cusp forms are signed in this way and in that way. So those weight to cusp forms correspond to the weight to cusp forms I said earlier here, F alpha. So I've now explained everything that I showed in the first slide in the elevator pitch. And so here's the context, which is the Langlands correspondence. The only thing I can do here is to try to repeat what I heard earlier because I did not understand those subjects well. But the typical statement of Langlands correspondence, to my understanding, poor understanding, is something like this. It is a statement for a pair of certain kind of groups, G and this Langlands dual, and a number field F. And then we may think of the representations of the Galois group of the field F with a value in the group G. And also, we may also think of a space of functions of this stuff. I'm not going to explain what is the ring of Adels or ideals or something like that, but here's the stuff of space with certain kind of topologies on it. And then we may think of a space of continuous functions from this space to the complex number. And for this space of functions, there is an action of the group of the Langlands dual L of G, LG with the Adel of the field F, whatever that is. And then one may think of the set of representations in that context. And then there's going to be a correspondence, or there may be a correspondence between the set of representations here and the set of representations there. I didn't understand those statements well, but presumably it is better to have at least the vague idea of what that statement is rather than having no idea what they are. So that's what I try to do. There are at least two cases where this statement has been established very well. One case or category is to set the group G and its Langlands dual to be the group of multiplicative groups, which is the set of non-zero elements, roughly speaking. And F is any number field. And the correspondence between the representation of the Galois group with the one-dimensional representation here, and also the function here in that context is regarded as Hecke characters. And so the correspondence between the Hecke characters and the one-dimensional representation of the Galois group, so that's abelian representation of the Galois group, in one-to-one. That's called class field theory. And that's established a long time ago. Another category where this correspondence has been established is the case where G and the Langlands dual is GL2. The field F here are the field of rational numbers. And then that's actually the Shimura-Taniyama-Veil conjecture, and it's proved by Taylor and Wiles. I've never read those papers though, anyway. And in that context, with the certain appropriate topology is given to this space, and then the space of functions in that context is now regarded as modular forms. So this is in the context where the modular forms are relevant. And so once again, so the representation has value. The representation of the Galois group has value in GL2, and the relevant number field here is the field of rational numbers. That's in the context where the modular forms are relevant in the Langlands correspondence. So when it comes, and in that context, the arithmetic model of algebraic varieties, or algebraic varieties defined over the number fields in general, can be regarded as a tool to generate Galois representations. So when we think of cohomology groups of those algebraic varieties defined over the number fields, and then Galois group acts on it, so the cohomology groups turned into a representation space, and we can construct the representation on the left-hand side. So that's a context. So in the case of elliptic curves of Shimura type, we can define the one-dimensional representation of the Galois group of the field of imaginary quadratic field K, and we may think of a induced representation of the Galois group of Q, which takes value in GL2. So then this is why those pairs, the two-dimensional representation of the Galois group and the weight to modular forms are relevant in the context of the Langlands correspondence. So that's the end of the mathematical background review. So let me continue to a more physics part or string theory part. So it is a natural question, I think, and I believe that it's a natural question to large number of string theorists, that the modular forms are there. So does the modular transformation in string theory genus 1 worldsheet have something to do with those modular forms or modular functions? In string theory, we may set those geometry at the target space. So we might think of setting those geometry at the target space and think of certain kinds of the correlation functions on genus 1 worldsheet. And then there will be many modular invariant or covariant objects. So do some of them have something to do with the weight to modular forms? So that's my question. And then here's a puzzle, actually, that one might encounter almost immediately. So to think of string theory with those geometry at the target space, we have to add some kind of information about the metric or complexify the Kähler parameters. But the L function must have anything to do, the L functions have nothing to do with the choice of the metric. So, but all the string theory formulation has to have, I suppose, well, except in certain kind of topological string theory, we need to include those kind of the metric information. On the other hand, in arithmetic geometry, even for a given geometry defined over the complex number field, we have sometimes infinitely many arithmetic models, which are mutually not equivalent to each other. And they have inequivalent L functions, inequivalent Galois transformations, and inequivalent counting of fractional points over the extension fields. So at least apparently, the L functions in the Galois representations and also the string theory seem to capture totally different information. So even though apparently there are modular transformation common, and yet those two different categories may have nothing to do with each other. That's a possibility, but still it's a natural, interesting question to ask. And actually, there is a pioneering work, early attempt in that direction, which is a paper in 2005. And those that paper studied some examples for elliptic curves with the complex multiplications. Two elliptic curves over C are dealt with. And for one elliptic curve over C, one model over Q was treated. And for the other elliptic curve over C, two arithmetic models were dealt with. Here there are a weight to cusp forms, so there are three of them. And the author of the 2005 paper tried to find a relation between those weight to modular forms with the parafermion characters and raised to multiple powers, and also multiplied by some power of Dedekind eta function. The parafermion models, are relevant to those geometry because those geometry have Gepner constructions. So to my knowledge, this is virtually the only work that comes in that context in the quest of the origin of the modular transformation. And yet, as I said earlier, there are infinitely many arithmetic models for given geometry over C. And also there is an issue of choice of the complex parameters. And there are infinitely many elliptic curves with complex multiplications. And only very few of them have Gepner constructions. So the whole picture is totally unclear at this moment. So I wish to understand it better. So that was my motivation. All right. So yes. So in principle, we may think of the whole problem of the origin of the modular forms with the arbitrary elliptic curve, comp CM elliptic curve, so the target space, but that is too difficult for me at least. But when it comes to the elliptic curves with the complex multiplications, the study in string theory is much easier because they are dealt with by rational CFTs. So here the rational CFTs, when we choose the elliptic curves with the complex multiplication of the target space. So we at this moment, I think of the set of target space, elliptic curves with complex multiplications sharing the same ring of complex multiplications in this context. And then the CFT is rational when both the complex structure moduli of the target space and the complexified scalar parameters are in one common imaginary quadratic field K. So, so the target space, the CFT is going to be rational, not just when we impose the information on the complex structure, but also on the complexified scalar parameters as well. But that's fine because that information, having the target space having complex multiplication, does not have a constraint on the choice of the scalar parameters. So we can choose the complexified scalar parameters in such a way that the string theory formulation is going to be rational. And moreover, I choose the complexified scalar parameter to be an integer multiple of the complex structure parameter Z. And because I have freedom to do so, that's enough. And then when we choose in that way, then the left mover chiral algebra and the right mover chiral algebra are identical, and a lattice VOA, and the lattice VOA, the lattice is given in that way. Okay, and the set of the irreducible representations of the chiral algebra are in one-to-one with the discriminant group of the lattice in question. And now, all right, so that's the setup. And then because this is the torus compactification in string theory, so that's one of the easiest class of string theories to study. So so now let me go back to the math background, and let me provide more technical details associated with the modular forms associated with the Galois representations. I said earlier that the modular forms in that context are Hecke-theta functions, and Hecke-theta functions are of this form. So it is the sum over the elements of the ideal class group, and the individual component to be summed over has an expression. They're just numbers, and it is something like a theta function, and that's why we call it Hecke-theta functions. It's not just the power series of it's series of Q with the exponent given by the sum of the lattice, but it is weighted by a linear function of an element in the imaginary quadratic field. So it is some variation of the theta function, but that insertion is still within the category where this theta function remains to be a modular form. All right, and there are technical details, but now we know what is the modular form. So and then when that function is understood with this level of the detail, and then it is not so difficult to identify which kind of the observables in string theory can reproduce this function f. So here's an answer. So we use a type 2 string theory, superstring theory, and think of the genus 1 amplitude or trace in the Ramon sector for each one of the irreducible representations of the chiral algebra. And we have ordinary time translation, Boltzmann factor, times the insertion of those stuff. And omega is the proportional to the operator of the one form of the target space, put back to the worldsheet. And it is normalized in such a way that the lattice of the vertex operator algebra is mapped into the ideal of the imaginary quadratic field. We can just choose the normalization in that way. And then, well, the individual component to be summed over the ideal class group has a relation with this class of genus 1 string theory observables in this way. We need to sum this kind of the character of different irreducible representations in a theory labeled by A. A ranges from 1 to the class number H. And that those characters need to be weighted by some kind of character, but that's it. And then it reproduces the theta functions with the linear function insertion. The linear function insertion is replaced by the insertion of the one form operator in the string theory on the string theory Hilbert space. So that's the idea, and that's the result. So here we have established a relation between the Hecke theta functions associated with the elliptic curves of Shimura type and the class of the genus 1 correlation functions available in string theory, where the target space is chosen to be the elliptic curves of the complex multiplication that we have started with. But there is one condition. We need to choose the Kähler parameter here in such a way that this divisibility condition is satisfied. There is a notion of a conductor for arithmetic mole, and we need to choose the Kähler parameter f in such a way that this ideal is divided by the conductor Cf. But this is fine. So when you are interested in an arithmetic model of Shimura type with a large conductor, and then we can choose the Kähler parameter f large enough in such a way that this ideal is divided by this conductor. So for any arithmetic model of Shimura type, we can find appropriate choice of the metric, Kähler metric, so that the string theory genus 1 amplitude reproduces the Hecke theta functions associated with the Galois representation. Now, here are some comments and observations. First, we use type 2 string theory rather than bosonic string theory. And this is motivated because we know that the Hecke theta functions do not involve the Dedekind eta, which originates from the excitation of the bosonic strings. So we designed the choice of the types of string and this insertion of the fermion operator in such a way that the bosonic string oscillator spectrum has an effect canceled by the excitation of the fermionic operators. And so only the theta function remains, and that theta function comes from the windings and closed lines. And so actually the observables here do not capture so much about the string physics, but it comes from the global aspect of the target space world sheet, and that they are measured by the windings and closed lines. So that's the first observation of what is being done here. And the second observation is that, and from the context of the Galois representation theory, we know that the Hecke theta, the theta function here, or the modular forms here, are supposed to be of weight 2. Independently from that observation, we have this observables in string theory, and we know that they are a weight 2 because if you're interested in the characters, then they are weight 0 under the SL2Z transformation of the world sheet. And this class of observables are obtained by taking second derivatives with respect to the chemical potential, one for the fermion number and the other for the translation on the target space elliptic curve. So that's the second derivative, and that's why this is weight 2. That's totally independent understanding of why this is weight 2. And finally, as a remark, there are observations elsewhere where we might add up the correlation functions of multiple different CFTs of vertex operator algebras. So because we need to take a sum over the ideal classes of the ring of integers of K, and the individual ideal classes are in one-to-one correspondence with the different isomorphism classes of a C of elliptic curve with complex multiplications. So what is summed over here, this theta with A is from one string theory, but the theta with the Ka with a different A are from different string theory, different target spaces. We need to take a sum over them to get the Hecke eigenforms and the Hecke theta functions. So this is a special case, nothing more than special case of a more broader observations of that category. And so we are just talking in that context of a very special case, which specifically corresponds to the modular form and Hecke eigenforms that corresponds to the Galois representation of the target space. So that's a remark. fine. And then
question. So it looks like you have a one-point function because omega is del x. If you consider multiple correlation functions, I mean endpoint correlation functions, what type of functions do you get?
there will be other parameters as well, place of insertions. We may think of the, well, I don't know, maybe, well, depending on the, well,
you take the string theory correspondence with the string theory seriously, then that's a natural object to consider. And it should be interesting object to study on number theory side too, I thought.
Yes. This is a very special class of observables available in string theory. And from the perspective of string theory, there is no theoretical reason to just to focus on this class of observables and forget about all other kinds of the observables. Then natural question is whether there are interesting arithmetic objects defined in the arithmetic geometry. I have no answer.
Okay, I see.
Interesting question. I agree. I do agree. I also wish to think about that. Also, Satoshi also was interested in that question, but we didn't develop that discussion further. We just didn't work hard enough. So that's where we are. All right, so fine. And then, so it's a possibility that that this is a part of the more broader story, and that would be interesting. But it's still possible, on the other hand, that I might just be saying that the Hecke theta functions are Hecke theta functions, because the observables to be reproduced from arithmetic geometry was known to be Hecke theta function, weight to modular, specific class of weight to modular forms. And we know that the theta functions are here and there everywhere in torus compactification in string theory. So I just took appropriate linear combinations to reproduce them. So I might be saying that Hecke theta functions are Hecke theta functions, nothing else. That's a possibility. There is one positive observation I can provide that actually this may be something rather than just an accident. And this is an observation. So let me go back to the arithmetic side. And then I said earlier that the modular forms corresponding to the Galois representation is a Hecke theta function. But there is one more characterization in the context of the theory of modular parameterizations. The idea is that the one forms are regarded as an object one form on the modular curves or one form on the Jacobian of the modular curves. And the Galois representations are on those one forms. So they are the generators of the representation space. And those one forms are actually regarded as the pullback where the target space elliptic curve has one form as well. And there are the surjective morphism projection from the Jacobian of the modular curves to the target space elliptic curves. There is a more well-established story for the elliptic curves, not necessarily with the complex multiplications, but are defined over the field of rational numbers. And then we don't have to have this factor K or other stuff. There is a straightforward, the projection from the Jacobian of the modular form, the modular curves to the elliptic curves defined over the field of rational numbers. And then the one form, the target space, can be pulled back by the projection morphisms defined over the field of rational numbers back to the Jacobian. And then they become the generator of the representation space. That's another alternative characterization. So the modular forms here are the pullback of the target space one forms. That's another way to think of those the modular forms in the context of the arithmetic geometry. Now let me go back to the class of observables available in string theory. And then that was the expression that we proposed. And here we have this is still the one form of the target space pulled back to the genus one worldsheet, although it has to be projected to the left mover, but that's still the one form of the target space originally. And well, we can just think of that, those characters on genus one is subject to the veil representation of the SL2Z transformation on the worldsheet, complex structure parameter. But the veil representation associated with the lattice has a kernel, the kernel contains the principal congruent subgroup with the level determined by the level of the discriminant quadratic form associated with this lattice. So we can bring this function of the complex structure of the world sheet to a modular curve, the upper half complex plane divided by the principal congruent subgroup. And then this combination defines a globally well-defined one form. And there is also, it is possible to identify this space of one form as a subspace, where the weight to cusp form of the gamma of n can be regarded as the weight to cusp form of gamma 1 of n squared in general. So this combination can be regarded as the one form well-defined over the modular curve of this type. The world sheet coordinate has been rescaled in that way by the level of the quadratic form. And then, so here, and the one form on the modular curve can be regarded as the one form on the Jacobian of it. So that's fine. So this is the same space, kind of the same space. But on this side, it has to be labeled by the Kähler parameters. But those spaces form a family labeled by this, the Kähler parameters or the level of the congruent subgroup. So we can think of a direct limit by those parameters of those the first cohomology groups. And so so the observables in string theory of this category can be regarded ultimately as a subspace of this direct limit, where we run over all kinds of choice of the Kähler parameters. So by taking the limit, the information choice of the Kähler parameters actually disappear. And all the class of the observables combined can reproduce all the kinds of the modular forms, which is the pullback of the target space homomorphic one form in that way. So because the modular forms in the same space can be reproduced both at the pullback in a biomorphism defined over the field of K, and also by the pullback by Polyakov path integral to the string theory. So this may be more than an accident, maybe just an accident. I don't know, but anyway, that's the observation I can tell you. Side remark about the papers on the Galois transformation on the S matrix in 90s and how this story is related. Because of the limited time, I think it is appropriate to skip it. Now let me go on to the discussion. First question, class of the category of questions is about still the same setup where the target space is CM elliptic curves, and on the arithmetic side, which we restrict our attention to the arithmetic models of Shimura type. This is still fine, and yet, well, I presented in a way that the class of observables here are, I said that this is the chiral correlation functions. It doesn't matter whether we choose the left movers or right movers. We can focus on one of them and calculate the kind of character with certain operators inserted. But there is an alternative of using the language of the open string correlation functions. And there, the boundary conditions are set to be the D0 brane Cardi states. And yet, at the level where we chose the Kähler parameters to be integer multiple of the complex structure parameters, the target space CFT is a rational CFT, and that is diagonal. And in that context, those two functions, the left mover functions and open string functions are the same. So we cannot distinguish which is the right interpretation. They're the same, so we cannot distinguish. But in a more general context, for example, maybe, or in a more theoretical better theoretical understanding, there may be difference, and maybe there may be better, open string version is better than closed string, or maybe the other way around. That's an open question to me. Another question is what happens when we allow ourselves to choose the string theory formulation to be non-diagonal CFTs. So the Kähler parameters can be chosen to be in the same imaginary quadratic field, but not in the integer multiple of the complex structure parameters Z. What happens? Well, what happens when we think about the CM elliptic curves? with the ring of complex multiplications, a proper subring of the ring of the algebraic integers in the imaginary quadratic field K. What happens? I don't know. I don't have the answer. I have not worked enough. Here's the second question, which is about well, how general this observation is going to be, and the well, even so, in the context of the Shimura, Taniyama, Vail, and Wiles and Taylor, so that story should hold for any elliptic curves defined over the field of rational numbers. So we don't have to require that the complex multiplication is there. And then, well, do we have similar string theory observables that reproduce the weight 2 modular forms? No idea, because we need to get started with the question, what kind of the criteria or characterization we are supposed to have for nonlinear sigma model CFT when the target space just happens to have the J invariant being algebraic. I'm sorry, the J invariant being rational numbers. So the broader question is, what is the property of the CFT when the target space has a complex structure so that the J invariant is algebraic? And the narrower question, more specific question, is what is the criterion for CFT where the J invariant is in the rational number? No idea, because in CFT, we tend to see things for left mover and the right mover, but now I'm talking about the properties in the complex structure and the Kähler parameters separately. I have no idea. Interesting question, but I just have really no idea. Now, what about the high dimensional generalization? So the easiest generalization is going to be presumably the abelian variety, K3 surface, and the Calabi 3-fold. And well, let me start from the known facts in mathematics and CFT. In mathematics, when we require that the abelian variety, an abelian variety or K3 surface is of complex CM type, a generalization of the complex multiplication, then it is known that the period of the ratio of the period integrals are algebraic, and also there are arithmetic models defined over number fields. And actually, the converse is also known to be true by now. There are the math literatures. There are not just a few to cover those statements, so I didn't cite them. But for abelian varieties in K3 surfaces, that's established. I don't know the state of affairs for the Calabi 3-fold and high dimensional varieties. Another known fact in CFT is this. So let's think of the even dimensional torus at the target space. I'm talking about the dimension over the real numbers. If the even dimensional torus target space is given by the rational CFT in string theory, then B field is rational. And also, when we focus on the metric, there is a finite cover by a product of CM elliptic curves to that the two-dimensional torus, the even dimensional torus. That is in a paper by Kathleen Wendland in 2000. So the direction of inference will be something like this. So the class of geometry will be defined, has an arithmetic model defined of the number field, and the class of geometry has the order ratio of the period integrals given by the algebraic numbers. And the intersection of those sets may be complex CM type, at least that's true for K3 and abelian variety. And for Calabi 3 and other spaces, maybe that's a small subset. And also there is the subtle relation between whether the nonlinear sigma model with that target space allows a rational CFT formulation by choosing the metric appropriately or not. The relation between, so the Gukov-Buffer paper asks about the relation between the CM target space and the rational CFT. That's the where we are. Now here's an observation. So the story that I presented here today is based on an observation that the Hecke theta function we can take a Mellon transformation of a Hecke theta function, and then it reproduces the L function. But this observation holds true only for imaginary quadratic field, and not for general CM field, which shows up in the context of the CM type K3 surface, abelian variety, or Calabi 3-fold. also another observation is that, well, we may have a representation over the field. Well, we got the GL2 valued representation of the Galois group over the field of rational numbers Q, because we got it as the induced representation of the Galois group of the field K. But this is the GL2 valued representation because the imaginary quadratic field is a degree 2 extension of the field of rational numbers. So we might have an abelian representation of the Galois group of the CM field of high dimension. And yet, if we think of the induced representation, then that's not going to be GL2 valued. So we don't have a reason to expect that its Langlands correspondence corresponds to a modular forms of any kinds. So when we think in that way, and then high dimensional generalization may be impossible, and the story that I presented here today may be just only about the elliptic curves. That's a possibility, but the other way to think is this. Well, so in the result of the Kathleen-Wendland in 2000, then, well, at least even when we think of the two even dimensional torus target space with high dimension, and yet at least metric-wise, it is isogenous to a product of CM elliptic curves. So in that case, it may be possible to introduce a complex structure to this even dimensional torus in such a way that the CM algebra of the cohomology of the complex torus has a CM type induced from that of the CM elliptic curve here that we have as a simple component of the abelian variety. So in that case, we have an imaginary quadratic field of the very basic stuff, the reflex field. So not so much about the CM target space, but about the rational CFT, at least in that context. And then, well, at least the imaginary quadratic field are relevant in this business. So there may be a hope, and we may be able to exploit this specific relation that holds true for the imaginary quadratic field. Another observation is for the Calabi-Yau threefold type 2b compactification. When we assume that the Calabi-Yau threefold is of CM type, and if you require that the flux with the supersymmetric and the supersymmetric flux with the zero cosmology constant is to be present in that Calabi-Yau threefold, and then, well, general CM type Calabi-Yau threefold is not enough, but the rational cohomology, the hot structure of the target space degree 3, the cohomology, has a CM type that is induced from the CM type of the imaginary quadratic field, and the imaginary quadratic field has to be given by the imaginary quadratic field extension, imaginary quadratic field generated by the Axi-Delaton the expectation value in type 2b string theory. Those observations are from my old paper in 17 and also another paper by 20 from Stanford. So I suppose we hear something related in a presentation by Richard Nally later in this workshop as well, from different or possibly similar related interesting context, I suppose. So here, once again, the imaginary quadratic field is the very elementary simple building block of the third cohomology group. So at least in that class of the target space Calabi-Yau threefold, and then imaginary quadratic field K is relevant as a reflex field. And so this specific relation may be relevant, I don't know. It's an interesting question, but I have not worked hard enough so far. So this is still an open question to me, an interesting question to me. So I think it's time to stop. Thank you very much for attention.
Okay, thank you, Taizan. Okay, so now it's time for questions or comments.
I have a question. Thank you very much for the very nice talk. In your main identification of the L function as a string theory observable, there was the sum. So the statement is that the L function is a sum over different conformal field theories. Can you please repeat that and explain that a little more?
Right.
Yeah, so it's about comment 3. So
right.
Yeah. Is it correct that the string theory observable is, meaning, is it an observable in string theory, or do you have to sum over different target spaces?
We have to sum.
And what is the interpretation of that in string theory?
No.
Okay. All right.
So so F here is the weight to modular form, but we need to take a sum over those stuff over the elements in ideal class group.
Right.
And the ideal class group elements in the ideal class groups, so the individual ideal classes are in one-to-one correspondence with the different elliptic curves over C isomorphisms, but sharing the same ring of complex multiplications.
Right.
So in the context of string theory, where we distinguish geometry with the isomorphisms over the complex numbers, they're different geometry.
Right. I see.
So those individual summands are observables in different string theory with the different target spaces.
I see.
There is no well, we don't take a sum over amplitudes in different quantum field theories. So
right, exactly. Yeah, right. Well, except recently there's been some discussion of that sort, but
right. Except in that context, we don't usually do so.
I see. So thank you. The other question I had was, I think immediately following this, so is there an interpretation of the Jacobian variety in string theory as some physical object in string theory?
No, I don't think so. Though the space of one forms are the same between the modular curves and the Jacobians.
But that seems to be the same as your title question, right? I mean, that they're the same. Is there I mean, once you have some Hecke theta function that leads to one form.
Well, because the modular curves have the Jacobi map to this Jacobian. So we can further pull back what you have on this stuff to the space of one forms on the modular curves as well. So, and then all of them are in the same space.
Yeah, I guess my question, not even about Jacobian, even the modular curve itself. I mean, usually we integrate over it. That's
right.
Okay.
To get the string S matrix.
Right. So the curve itself, I mean, is there, if I have a one form on the modular curve, does that have a meaning in string theory?
Well, because if it is a well-defined one form, we may think of a contour integral of that one form.
Nice. Okay.
What is its physics interpretation? That's your question, right?
Yeah, exactly.
I do not know. I don't know. I have no idea. Interesting question, but I have no idea.
Okay, thank you. Thanks.
Okay, further questions?
I have a question. Can you hear me?
Yeah.
Yes, I do.
So in the case of the K3 surfaces, did you have any particular construction in mind? Or for example, you consider K3 surface of Kummer type, which in principle can be written as the product of two elliptic curves endowed with CM. Is that what you had in mind when you said K3, or?
Well, that's one of the class of examples. And then, so that's going to be the easiest class to find the candidate of the observables, because we know the string theory very well. The literatures on the CM points on the K3 is enormous. And so there is a fairly good mapping between all the CM points in the period domain and the K3 complex structures as well. But the recovering the string theory spectrum on that CM point may be a little bit difficult in general.
Okay. Yeah, perhaps we could talk about this next week.
Yeah.
Okay. And one more question. You mentioned somewhere that, did I understand correctly where you said that there was a point where you said there's no understanding of the weight to eigenform? Or perhaps let me rephrase my question. The weight to Hecke eigenform that the weight to eigenform that you get out over here, is that the same one that Richard and Shamit and Wenger write as the way to eigenform coming from the supersymmetric locus in their paper?
I think so. That comes in this context, the last one.
Yeah.
So they consider Calabi 3-4 as target space. And so in general, Calabi 3-4 degree 3 cohomology is of multiple dimensions. But the Hodge components include 3, 0, 2, 1, 1, 2, and 0, 3. And a part of it, that the degree 3 cohomology contains the Hodge structure of level 1, which means that there is the Hodge substructure which contains only the Hodge component 2, 1, and 1, 2. And in that, the subrepresentation, so they discuss the action of the Galois group. And then for the Galois group action, we can think of the L function from its characteristic polynomials. And then for weight 2 modular forms, so we can think of the modular forms. So that's the arithmetic side. Separate question is what kind of the string theory observable that reproduces that the modular form. That's a separate question. So that comes in this context.
Sorry, the last part you got cut out a bit. That's a separate question, but?
I'm sorry?
I think the last part you got a bit cut out. Or my internet was gone.
Calabi for Calabi 3-4.
Okay.
Okay, there's time for one more question if there is one.
If no one else has a question I would like to ask, but if someone else, please go ahead.
Yeah, yeah, why don't you go ahead? Yeah.
Yeah, it was, you made some comment about the Galois, the interpretation of the Galois action in physics, but you said you didn't have time. Can you say what you wanted to say?
Presumably you're talking about this.
Yeah.
All right. Back in the early 90s, people studied the rational CFTs, rational vertex operator algebras. And then there are finitely many irreducible representations of the chiral algebra. And on top of it, for example, for those characters, the SL2Z modular transformations acts through some representations. And then we might think of just thinking of the Galois group acting on the matrix elements of the representation matrices of S transformation, T transformation, stuff. In the case of a rational VOA, those matrices turned out to have the matrix elements in the rational algebraic numbers, so we can define Galois group action. And the various theory has been built on it. And then in a paper by De Giovanni in 1994, and then the argument was that it is regarded as a part of the Galois-Teichmüller theory. So Galois-Teichmüller theory, well, in my very poor understanding, I'm sorry. We may think of the upper half space divided by the SL2Z, but we can also think of various modular curves. And then for modular curves with the proper congruent subgroup, they can be regarded as a covering space over the upper half space of SL2Z. And all of those varieties actually can be regarded as algebraic curves with the field of definition in the field of rational numbers Q actually. And so we can also think of the action of the Galois group on those geometries and Galois transformations. And the Galois transformations also act in the form of the covering transformation, changing the layer of the covering space. And so the paper by De Giovanni in 94 interprets the discussion by Dubois, Gary, and Coste-Gannon and other people or the Galois group action on the matrix element of the S transformation, T transformation as a part of the story of the Galois-Teichmüller theory. The Galois group acts on the the ratio of the quotient group in the covering space. So that was that theory. And so what I presented here today was that so that theory was about the Galois group action on the S matrix and T matrix of a rational VOA. But we also think of the observables available in rational VOAs, and then that's they are functions of the complex structure parameters of the world sheet, and they can be lifted to the modular curves. And in the context of the Galois-Tahi-Miller theory, the Galois group also acts on those the modular curves as well. So and that action induces the Galois group representation on the entire cohomology of the modular groups. So that's a part of the theory of modular parameterizations. So the relation between the theories in the early 90s and what I presented here today is both the part of the Galois-Tahi-Miller theory, and what I talked about today is a part of the sub-representation. And the discussion in the early 90s is regarded as a quotient representation of one of the big representation of the same theory. So that was the observation.
Okay, all right. Okay, thank you very much.
Okay, so I guess it's time. So let's thank Taizan again.